So, good morning, everyone. First of all, since we cannot have this class physically due to the exam schedule and everyone's different schedules, we are planning to put out a recording video, and this will be for the case of LoRA, which is low rank adaptation of large language models. Again, like the previous classes, I do not have any slides specifically, but I would like to discuss, quickly revise the concepts before. I do know you have a quiz today, and all the best for that. So, the main concern is how did LoRA come up, right? So LoRA didn't just come up directly for something which was previously already there, right? So there were some concepts which were going around, and then the concept came up. So if you look through the paper once, which I highly suggest because it's a very simple paper to understand. So these models, right? What do? They try to do some representational learning, right? So you map from higher dimension, you keep on going into a lower dimension, right? You start from like 1024 linear, and then you have a final embedding of 512. So what people try to do is try to see how the weights change when we try to fine tune these models. So what they notice is that the when we do the fine tuning of these models, those matrices, the delta matrices, the weight matrices which changes, the entries are pretty sparse. They're pretty less. That means most of the matrices have rows which are linearly dependent. So this is again back to your linear algebra concept, right? So what was rank of the matrix? That is number of linearly independent rows, right? That was the concept in your linear algebra course. So what happened is that these matrices, which the delta matrices come up, most of those matrices are dependent. Most of those entries or the columns are dependent. If you say it's a column rank, or if for in case rows for a row rank, most of these entries, what you realize, are dependent. So why do we need to maintain those state? What if we maintain for one and then keep? So that is one of the intuitions behind LoRa. So I've already highlighted it that one of the papers in 2018 and 2020 shows that the learned over parameterized models in fact reside in a low intrinsic dimension. This is exactly what the line means, and this is actually is the core idea behind LoRa. And their hypothesis, the author's hypothesis, is that the change in weights which happen during model training or model adaptation has intrinsically a lower rank. So when you take this observation, you need to also come up with the fact that how are the fine tuning steps happen. So initially you have a weight matrix from your pre-trained model. You have a task, cat and dog or bikes and horses classification task. You train your model, your weights change by a little amount. And how so what are you storing? Let's figure out what are you storing in the GPU first. In the GPU, you're storing your default weights, the weights of your pre-trained model, around 3-4 GB, maybe 5 GB. If you're using Google's Gemma model, it's 5 GB of weights. Then during the model training process, you are again taking a copy of those and then trying to update those. So you're anyways maintaining some list of weights which are changing, and not exactly all of you're maintaining all of them. So you're using another 5 GB of storage to score to find out the gradient descent, the weight differences, and obviously some other variables which the algorithms require. So that's why your model weights, if it is around, it is very high. When you try to train the model, there is a space taken by the pre-trained model weights which will always be there, and during optimization it even explodes because of the PyTorch graph storing each and every node, storing the gradients as well as the weights are being the current variable w, right, in your gradient descent, where is w equal to w minus alpha times grad the loss function. So that w is also being stored, right? It's a running w, so it has to be stored so that you can keep on removing. So that's also there. So that's the thing. So how can we decompose this equation? A very intuitive way is you have w, you have another matrix called as delta w. Okay, so delta w is basically something which consists of the delta, the difference in the final weight and the current weight. So what you can do is you can have w plus delta w, which is the new weight, and transpose x. That's what you do, right? W transpose x is equal to the output label or anything like the output logit in a linear layer. So we do that. So what we'll get here is we'll get w transpose x plus delta w transpose x, right? The w transpose x here is already same. So do we have to keep bothering about storing it in memory? Do we have to cache it? No need, right? We already have w because we loaded the model from like PyTorch Hub or HuggingFace. But delta w is something which we need to take care of. Now the interesting part here is, which I'll go here, I'll quickly skip this part through. Yeah, this is the equation which I'm talking about. This is the equation. So if I highlight it here properly, this is the equation which I'm talking about. And this is again the same dimension as what W naught is. That's why you can add the matrices. X is X itself. But the interesting part is their hypothesis is that this delta W has a lower rank. So what I can do is a rank decomposition. This is very similar to what singular value decomposition, anything you can do. So what I'm saying is that I can make delta W into two matrix B and A. Suppose the weight matrix is 75 cross 75. I say that the weight matrix, the delta matrix, has a rank of 3. So what I mean by that is that B can be broken down into 3 into 75, 3 cross 75 matrix, and A can be broken down into 75 cross 3 matrix. Right? Is that making sense? So try to take it in. So when you check the number of parameters, which I can show you, 75 cross 75 is around 5625 parameters. So if you take 3 cross 75 plus, okay, so consider that to be B, and you can take 75 cross 3, which makes it 75 cross 75 itself. And if you add them, it's only 450. It was around, so 450, and it was around what? It was on 5625. And if I divide it by 450, it's almost 13 times less. Almost 12 times, let's take. It's almost 12 times lesser. What are the advantages we have? Number one, we have lesser parameters to train. Number two, we always have lesser memory. It will take less memory to do this. You have W naught already maintained. You need B and A to be maintained. And you can do the multiplication operation. Like these are, again, this multiplication is faster. Why? Because they're in between smaller matrices. So that's why. So, and they've defined the mathematical constraint of how rank R should be chosen such that it's minimum of the dimension of the model and the K, and there are other things. You can read the paper to understand. So I'm coming back above again. So what our class, suppose we are doing a classification problem or a prediction problem where we have a log likelihood. So what our problem boils down to, earlier we used to say that the probability is over the parameters theta, and we calculate the likelihood. Now it is parameters plus the delta parameters. So theta, or here they have written phi naught plus delta phi naught. That's what I'm trying to say. The thing which I have shown here, it's just written in a mathematical form which looks scary, but it's very simple to understand. If you understand the basics of how log likelihood, how the next token prediction is working. So this is what exactly we try to figure out. So in short, that's the core idea of LoRA. In inference, what would you do? Suppose you're storing, you have trained the model using LoRA, what would you do? You store the delta W in your repository. You already have W from the base model. So when you do a load there, so you should notice that when you save models using LoRA, they're in 3-4 MBs. Your original model was around 6-7 GBs, but your LoRA based model, the PEFT model, that's the order in MBs, which is very small, and it's easy to travel around also. Like you can easy to move around various devices and all. So what happens here is, when you load the model, it will first look, it will have some YAML file, it will have some JSON file, it will look at the file and figure out what is the base model. Suppose GPT-2 is the base model. It will load GPT-2, which is again 2 GB or 1 GB, whatever it is, and then it will prepare the delta Ws. What you can do is inherently add the delta Ws there, and you will get the new updated weight matrix. And during inference, use that to do your predictions. Easy, right? Very simple concept. It just came on the fundamental assumption that the differences of the weight matrix have a lower intrinsic rank, and we can exploit that. And obviously this hypothesis worked. That's why this paper is so popular. Otherwise, obviously it should not have been. If it didn't work, people would have not. People tried and they have seen that it works. So they have shown how they have applied in any subset. So LoRA, again, in principle, you can apply to any of the layers of the transformers. Linear layers is very optimized heavy, because even in our CNN tutorials, we've seen that the linear layers are taking most number of parameters, not even the convolutional layers. So you can apply to any kind of models. Transformers they did because why? Because all the generative models were becoming popular and they were becoming tough and tough to train. It was taking days and days, even taking months. So now you and using the GPU. So now you can use a single GPU and you can easily train up to 2-3 days, which is actually less in terms of the training market which we currently have in machine learning research and machine learning softwares. So they had done some experiments. So let's not dwell too much time. It's a 26-page paper where they've explained what is better, what are the current techniques to fine-tune model. There are some extra information also. So if you read the initial part also, you can compare. Also, do note, your rank as you go higher, your performance, your accuracy and other performance might get better because you're approximating less. You should understand that. So why am I telling you this? Because for the fact that when you are actually like training your model, you might be able to play around with the rank parameter. So that might help in your project, maybe help in your some other activity where you're okay that you need a little bit of optimization. So it's basically an optimization and a performance curve, right? So when you're over approximating, over rank, like you have made the rank so small that you are believing that only 3 rank is enough, a 3-dimensional rank is enough, only 3 vectors should be enough to define that space, define that whole delta W subspace, or I think say a linear space as well, not linear space, let me correct, it's subspace. So in that case, you need to be actually careful about how you modify the rank parameter, and you might lose some performance based on it because that's an assumption, right? That's a hypothesis. You can go wrong in a hypothesis for your case. So you might have to increase R. So what happens when you make R equals to whatever D was? You'll get back the original concept itself. If you do a full rank, that means you're taking the entire. So there is no point in W naught plus delta W. So B and A will be smaller in number, and yes, you will have. Will you have lesser parameters? No, you won't have lesser parameters. You would rather have twice the number of things to maintain. So you're increasing your memory consumption. So that you can figure out. You can take a pen and paper, you can write the dimensions, you can figure out how much memory has been consumed. Okay, let's not dwell about it more. So before now that we are done with the basics of the paper, let's try to figure out how to use the library. So we'll go to the PEF library in HuggingFace. So here, so HuggingFace has already implemented LoRA for their models. Like LoRA is written by Microsoft Research, so they have their own repository. Maybe you can try that out, but mostly when people are using it, they use it with HuggingFace. So this is the main guide page, and you can check. So if I go here, each PEF method to train is defined using a PEF config class. So you can click on the config class, look at all the parameters what you need to understand, and you need to understand all of this. And most of these have very simple explanation, and the rest are very complicated. So it's very use case based. Some of the important are task types. So what do you want the LoRA model to be initialized for? Maybe sequence language modeling. So basically T5 kind of thing, or maybe generative causal LM like a GPT-2, or maybe text classification using BERT or anything. And then whether you're doing inference or you're doing like training. So that's also important. Then this R, that's why I was talking about rank. So this is the rank, what rank to go for. They have done 8. And then there is scaling factor LoRA alpha. So this alpha, right? That's why I had the paper open. So there is an alpha factor here which they talk about, which is a scale WX. So they're divided by, like scale it by alpha by R, where R is one of the rank and alpha is a constant kind of thing. And this is like a hyperparameter tuning, like a learning rate kind of thing. So how do you scale the deltas? So that's also there. And then there is dropouts if you need for the LoRa layers, if you want to add some dropout layers or something for training the delta W thing. So once you have that ready, you can just like load your model, and then there is a call of get PEF model. So you pass your model into the PEF model wrapper with the PEF config, and it will apply the LoRa layers, and then it will output all the trainable parameters. So the way they have done it, I think this is one of the, some MT0 large model, and out of which only 20% is now trainable. And it is a 1.2 billion parameter model. So you can already see the number of optimization. Or it's not 20%, so my bad. This is 0.20, like 0.19%. And then there is one inherent problem that if you use HuggingFace PEF, you might have to play around with the trainer a bit. If you are the classical guy who likes to like implement the entire training loop, might or might not work. It should. So you should actually like Google a bit and see how you can like take it as a challenge. Google it, how you can use PEF as well as write your own training loops and try to do your own things. So you can see the training arguments, how it works, and the trainer. Fine. So there is a lot of things, and actually trainer is not actually a very bad thing. So I would not say that you should avoid it at all costs. No, you should actually try to understand it. So because if you set up this trainer correctly, most of the things will be done. Even logging is handled in trainer. So you can use TensorBoard or WantB. So do try using TensorBoard. I highly suggest. It will really reduce your time in creating plots. So do take some time to learn TensorBoard. It will help you later when you take PEs and REs and other, when you're writing papers, you'll be very easily like handle things. So okay, so yeah, so we did okay, I switched to a wrong tab, so that's not a big deal. Sorry about the configuration. Yeah, so now this is the trainer thing. So this is very basic for it. So other than that, what you should do, you should obviously check out how the configurations work. These are all the options for LoRa. What can you do, dropouts, what to save, what not to save, and all those kind of things. Target modules, this is important. So okay, let me get the example first where I can show you the target modules. I think it's an integration, so I'm very sorry, I'm switching in between because I haven't. Yeah, so they show this for a diffusion model, how they're doing it. You can look at the examples, various methods here. So I'm just trying to show you where, So PEFT in general has a lot of tools, okay? It has some prompt based methods, it has some IA3 methods. So these are different papers they've implemented, and this is then LoRa. So for LoRa, how would they do it? So for LoRa, they have installed, they've loaded the data set, and this example I'll be showing you in notebook in practice actually. So there we are going to talk more about it. So yeah, here. So this is the main developer guide. So developer guide is where you want to write custom things. So this is much more detailed. The rest of all these are easy to use kind of simple notebook ideas. So again, yeah, so how do you load the model? So this is again a small revision and it will be done. So I would like to show how can you do a custom kind of thing which will actually help you. uh, okay, sorry, custom models, yeah, why not? So you have your own perceptron, you want to add some LoRa layers here. So you have to see the named modules. What are the name modules of the ML model? And then you will see this sec0, sec1 and all, because these are all linear activation relu. So what they are, so you want to apply to some of this, suppose sec0 and sec1. So where you are writing LoRa config, right? In target modules you need to write these names. Sorry for that. You need to write the following names. So in that case you need to be able to yeah, so in that case you need to be able to figure out which modules you actually need to do and which modules to save. So you can go through the documentation. That's what I want to show you, that if you ask me that how would you do a custom kind of thing, this is how you do it. You check, you take which of the target modules you want, and then what more is there which we can discuss. So these are different adapters possible: LoRa, prefix tuning, prompt tuning. So you can check all these methods, and prompt tuning and all these are very popular in LLMs, kind of study of LLMs. So if you're very interested into the LLM hype train, I would suggest you to do that. So other than that, there is one thing called quantization. This is important, that's why I wanted to do. So quantization model, right? So I had already talked about in class, right, that these models are large, and we were talking about the optimization in the last part of our class, right? So there what we did, we said that we can, you reduce the number of bits, we'll sacrifice some precision and have some lower memory storage kind of thing, right? So we try to do that. And in that case, this is the example where they show. So quantize, if you quantize a model and try to train it, usually they notice some kind of loss, and obviously there was some loss in performance, but most of the use case there wasn't very big loss, so people still did it. They were able to do it on their community GPUs like T4, P4, X2, and all those GPUs were available on Kaggle, and obviously the RTX 3090 kind of GPUs. So LoRa, but doing it on LoRa will just, if you do those weight decomposition and multiply, and you already have lower precision, you might get a little bit of more error, which might like brings LoRa's performance down. So there was another paper called QLoRa which was introduced. Will not go through QLoRa's paper review here. So you can clearly like easily check the paper and what they have done extra on top of, they've already used GPT-4 also for it. So yeah, so how they were able to do it and all, and what extra things they have added, so you can check whether there are some bit manipulation, how they can maintain the precision, how can they maintain, so those kind of extra computer precision methods they have used. So that's the thing of a QLoRa. So how do you load that, right? So there is a package called as bits and bytes config. That's why I was talking about it. So I wanted to introduce bits and bytes to you. So bits and bytes is a package which actually implements the quantization in transformers with transformers. So there you can have some different parameters. So you need to check the meaning of all this. And usually load in 4-bit or load in 8-bit is something which is the most popular parameter used. So there they pass this config and this model, the size also reduces of the model. 5G model was actually the FP32, FP64, FP64 thing. So we bring it down to FP16 and FP8 precision. So floating point. What I mean by FP is floating point. And then you try to use this bits and bytes config to bring it down and use QLoRa for it. So be careful. You can use LoRa, but it won't perform well. So use QLoRa for it. So again, QLoRa calls will be very similar. It's just a wrapper on top. So for that, if you want to do so in so this model, you can just pass the quantization config. So in place of using what it's called the LoRa call, before you pass it through the LoRa wrapper, you have to pass it through a KB training wrapper. That's the extra step you need to do so that the function can be pre-processed for some the quantization training, and then you do a LoRa config and then you pass it. So it will automatically set however you want to do. And there are some other style training. So for QLoRa, you'll have to see how to do it. So QLoRa adds trainable weights to all linear layers in the architecture. Since the attribute names of these linear layers can vary across, so they created a module for all linear to add LoRa to all linear layers. So QLoRa style of training you can do. So because of that quantization wrapper, right, bits and bytes wrapper, and the prepare model for K-bit training, you can apply LoRa and automatically it will follow a QLoRa style accordingly. Okay. So this is much for the theoretical whatever. Like it's not even theoretical. We are just I'm showing you around how to maneuver under docs and find the answers better than ChatGPT or Gemini and then having too many errors to handle. So now I have a demo on a vision task. Again, this is a code I've just written few moments back, so I'm not very sure it will work or not. So we'll fix the errors along the way so that I can show you how machine learning debugging also works. So before you start, you need to know that there's an accelerator option here. So you make it GPU P100 and I start the model. And obviously these are basic imports, and since I want to push this model to HuggingFace or I want to use something, I can use something as HuggingFace notebook login for Jupyter notebook. So once I start this, I'm waiting for Jupyter to start up. So so they will ask for a token here for the notebook. So how do you generate it? You go to your profile. I'm logged in HuggingFace, and then if I click here, I can go to settings, I guess. Yeah, settings if I go, and I will go to access token. So these are some of the tokens I have. So I can just create a new token called as demo video. So I'll delete this token so you don't have to worry. So I just do a write token. So you can do a read token also. I have a model read token which I use, and because I don't want to overwrite some of the models sometimes in HuggingFace. So I'll take a demo video token. It's asking me for the token. I'll paste this token, and add token as git credentials. You can, and sometimes like I have to repeatedly enter the token when you're pushing. So I've done login. I'll not save it. So then I have model checkpoint. I'm using a vision transformer here. So I'm trying to classify food here. So this is a very popular food data set. And we have taken only some of the data here. So you can see train of 5,000. So I have taken only 5,000 samples to fine tune it on so that we don't have to, because see, this is already 500 MB data set. So probably you can try this also. I think those who are having problems of taking a sample. So if you know what's the size of a total data set, why not try this syntax? I'm not sure whether it will work for your project or not. So HuggingFace also the data sets are organized in specific way so that this works. So I think I would still suggest if possible you can do it. So this is again a very large data set. They've sliced it up into chunks of 1, 2, 3, 4, 5, 6, 7, 8 as I'm talking, 9. Okay, that's a lot. Okay, so I think it will download everything and then slice. So there are like 10, 11. It's keep on going. So it's at least 6 GB here already. So now they're generating, this is a 75,750 kind of a data set. This is a large data set, right, on HuggingFace. So they have taken this 5,000. So please check whether this kind of syntax works, or just Google around and see how specific split works. This might actually be useful for your assignment, this kind of syntax. So again, these are some of the pre-processing steps where I have to map the IDs of the food to the name and name to the food. So basically I to S and S to I, right? So it's text classifier gives a text output. So I'll get a number and I'll have to pass it to a dictionary, that kind of thing. And then obviously for transformers or vision transformers, you have something like image processor text, you have tokenizers, so something similar. So that's what I'm trying to do. I'm hoping that this is GPU optimized, but let's see if it's not. Okay, and then you have the image processing. These are all the augmentation things which you try. And then obviously I'll create the splits of data set and everything. And this is some helper methods. So this is an auto model for image classification. So I'm using a vision transformer. So these wrapper models you need to explore on your own, because if you go on taking another lecture on it, then this video will become hours long. So if I check, this is the number of trainable parameters, 100%. So I've not applied LoRA yet. So this is where the LoRA part starts. So now you can see, right, what's the LoRa config, what I did. I can change only 0.77%. Now will be trainable. Earlier you were training all the, how many, what's the order of this? 3, okay, 1. 10 power 7 order, and now you're just training 10 power 5 orders. So you went down few orders and it became this 0.77%. So now this is the training arguments thing, the trainer thing. How do I do it and all the things? What is the epoch? How do I evaluate? How do I save? So per epoch is going to save. And how many epochs are there? That's interesting. I'll have to see. And obviously there's some metrics which you need to load and all. That's all. Collate function, you need to present the data to the model in such a way. So how does the vision transformer take the data? You'll have to see example pixel value. So they had to stack this and then figure out. So that is obviously every time when you're using this, any of the HuggingFace model, read their documentation. It's going to take 10 minutes, but it's going to save hours of debugging. And they will mention what collated to write. So you don't have to be very scared about it. And then lastly, I'll do the train.train and it will start training. Okay, this is for 1B, I think. So if I, okay, I already have someone else's 1B key here. So this is just for experimentation. So you can change the trainer arguments to have a tensor board kind of logging. That's also possible. So since it's a Jupyter notebook online, so they automatically take 1B for it, but no need to use 1B. You can change it in the training arguments function. You can just Google while it trains, tensor board training args, get started trainer. Okay. Oh my bad. The report to, right? This is, you can see where you can do Azure ML, Comet ML, tensor board, won't be, use all to have all. So you can just use report to parameter, report to thing for set logging. So that kind of thing you can do. Strategy. So they have set it here. So you can dictionary, you can write the same thing. That's what I'm saying. If you expand all of this, you can actually find where you want to do, where you want to understand which of these things. So expand one. I think this will give you the answer, to be honest. Logging dir, so you can add tensor boards logging dir, so automatically it will handle. Report to, so tensor board. So that's it. So don't have to worry too much. And this will take around 5 minutes. So you can just check where it is going on in HuggingFace and everything. So I would love to have it till completion, but I think this is something which we are just wasting time on. So there is an eval log which is coming, so the accuracy will keep on increasing. So in between every epoch, so this is epoch 1 out of 5, right? So every epoch there is an evaluation loop run on the eval data set. So we can see that how the validation loss is there and how the accuracy is going up. So this automatically logs it for you. And again, this process slowed up for some time because of it, and see how much memory. It's already consuming 12. So imagine you were trying to do a fine tuning without LoRa on it. It will definitely accident. This is I'm using a community GPU, a free subscription for Kaggle. So that's the thing, right? So let me interrupt it for now. And can we evaluate it? Let's see. Let's see, will it evaluate for us for the half trained broken up model? It actually did. So the variable is stored, right? So this is the accuracy which is coming. This is already good. So, but still, if you click on this, it will save the model to your working directory. I think I'll have to wait. Yeah, LoRa model VIT based something. So this is the LoRa model which will be stored. And this is what it exactly is. Okay, this is how I intended to store in won't in the trainer. So that's where this file came. So this LoRA model, right? This is all the files. I'll have to wait. Yeah. Adapter config, adapter model. So it's not storing the W's. It's only storing the delta W, which is known as the adapter weights. Okay. So that's clear. That's easy. So that's what the demo is about. So there was one question of how to run on backend. So I used to say this, run it on the Kaggle backend. So you need to click save version here, go to advanced setting, run with GPU file sessions. You do a save and run, commit. See if your code is right, which usually it should be. And since there's a notebook login, it is a blocking step. So that's an issue. So I'll just disable the notebook login. So if I do a save version here, save and run, I'll say trial one. You write the hyperparam names. If you want to write hyperparams, date, whatever name you want to give, my model, and then you click on save. It will show this event. So this is a running notebook. So as soon as that's done, you can stop your notebook, let it run. Click here. So I'll close my notebook. See, this is the notebook. So it will show, because since it's running, it will not show you the notebook how it looks. It will come at input. So it will show what data is using. Output is that output folder, right? Remember the output folder? So that output folder, whatever they are, it will show here, and you can download them as a zip. So there are logs which will show up what logs message you have logged in the notebook, and there's obviously comment. So suppose you have closed this thing, how do you check it? So here, this is your code page. You go to your work, you can check this, and then you'll see the same page. So yeah, that's it. That's for the demo. If you're listening the entire time, thank you, and hope you have a good quiz today, and hope you're able to do the project well. Yeah, thank you.